be set up with number 61 because it's just slightly different than what we're used to. The function that they give us is a function with respect to y. So y has become the input, or in other words, the independent variable. So this is what our x-y table looks like. It's now a y-x table. So if you were to plug in y into our function, we would get 0, 0 squared. 1 squared is 1. 2 squared would be 4. Our directions were to find the area between the graph and the y-axis this time. So we're going to have to sketch this. So now keep in mind that we're going to be moving vertical movement first for these points. So it's 0, 0, 1, 1, 2, up 2 over 4, and then up 3 over 9. So if you can kind of see here, we have half of a parabola. Instead of being up and down, though, it's being vertical. Right. They gave us inequality notation. I rewrote it as interval notation. So what they're saying is on this y-axis, what we're going to do is we're going to cut it off from 0 to 3. So I'm going to go ahead and draw in this line right here. So find the area between the graph and the y-axis. We're trying to find this area right here. The thing about this is we are still going to be using that same limit as n approaches infinity of the sum. But now, one thing that's going to be changing is our c sub I, and instead of looking at delta x now, the widths of the rectangles that I can possibly draw now are going to be delta y's, because if you can kind of imagine, remember, we're going to split this interval from 0 to 3 into many pieces, but for the purpose of this, I'm going to just do it into a few. So let's say that this was how many. These were infinitesimally small little sections that I'm splitting this interval into. And when we draw those rectangles, I had rectangles, I know. Okay, when we draw those rectangles, that's what it's going to look like. So the widths now, instead of being the widths of them, they're on the side, they're laying on their side. So delta y, these are all our little delta y's here. So there's a delta y, there's a delta y, and so forth. Okay, and then don't forget our c sub i's, those are now going to become the y values along the y-axis that we're going to be plugging into this function in order to get, alright, what is this point right here. So, I mean, let's look at this first delta y, that would be f of the first delta y would get us this point, this height, that's now horizontal of that first rectangle. The second rectangle, it would be 2 delta y's. Then we would plug that in and we would get that value on that graph. And then same thing here, this would be our third delta y, and so on. So we're going to use the same exact formula, except for keep in mind delta y is going to be now using these upper bounds and lower bounds, 3 minus 0, and then we're going to be splitting it into many, many little pieces, so we're just for now going to call that n. So delta y is equal to 3 over n. Alright, and then c sub I, like I was saying when I was going up here, that's going to be our index number times however many delta y's that we're interested in, so it's going to be delta y times I. So, in other words, 3 over n times I. Alright, so our final say in this is I'm going to plug this all in now. We have a limit as n approaches infinity of f of c sub I. So this piece right here we're going to plug into our original function. We have 3 over n times I, okay, squared. That right here is this, and this being plugged in. And then times delta y, so this piece right here, which we determined was 3 over n. So now you need to just go about this, solving it like you would usually with the same setup that we had before. So I will say, make sure you distribute this. It's going to become limit as n approaches infinity of 9i squared over n squared times 3 over n, and these also can combine. So just pull out the constants that you can. Now what we have to discuss is your book is about to transition you into the long way that we once were working on. We're going to now be instead of doing this limit function, we're going to be transitioning into just doing basic integration. So we need to make that link that the limit approach that we've been using is equal to just integration. Because when we discussed this a while back, but integration, besides just finding antiderivatives, integration can be used. Integration can be used to find the area underneath a function. Okay, so what we have is, we for a while have been using this to find the area underneath a given function over a certain interval. We've used this. Okay, now what we're going to start to do is transition into using integration to find the area underneath a curve. So in order to find the area of a function, of a particular function, over the interval with a lower limit a and a higher upper bound b, lower a and upper bound b, this is what we're going to use. Okay, so besides this shortcut, which you're going to find is a lot quicker than doing the limit approach, we also have other shortcuts that we can do. And the shortcut includes, if you go back to our very first example, we did the limit process. We did the limit process on this function f of x equals 3x. All right, and what I hope you could see is right away you didn't even have to do that. If I wanted to find the area of this triangle, we could have just used the area of a triangle formula. So I do want to bring up this slide, and please do write it down. Unless your directions specify otherwise, what you should be able to do is, if you recognize a graph as just some sort of rectangle or square, and that's where, if you ever have a constant, you're going to have some sort of rectangle or square. Linear equations, they produce either triangles or rectangles and triangles. Circle equations will produce parts of circles. Absolute values, they're going to produce triangles. Whoops. So the idea is, so if you ever are in the position where you see just a geometric figure and you know the formula for it, use it. Alright, unless your directions in your book say otherwise. Alright, so like I said, your book is now transitioning you into using shortcuts. And for number 3 and 6.3, what they ask you to do is evaluate the definite integral by the limit definition. So I'm going to rewrite this as the limit of a Riemann sum. So here what we have is an integral, all right, and then we're going to be talking about definite integrals versus just regular integrals, indefinite integrals that we've been most used to. But what we have is an integral that's bounded by from 4 to 10. We can always, this is just saying, find the area underneath a function called f of x equals 6 that's bounded by this upper and lower bounds. So the same thing we could use is the limit. And then our function, our f of c sub I, really has no index number. It's just 6. So we have to write in 6 and then delta x. So all in all, really, this whole thing is going to be replicated, except for we plug in a delta x for this dx, and if we had an x, then we would put in, like if we had 6x, we would have put in 6 and then c sub I. Okay, so here, this is where we're going with that. There's one other piece that I can fill in. I know that my delta x would be my upper minus my lower bound, so 10 minus 4, they give it to us in that notation. 10 minus 4 all over n, so what I get is 6 times, and then this simplified would be 6 over n. Alright, now I need to go through and simplify this, pull any constants out that I can, and I can. This is 6 times 6 over n, and that itself is a constant. Notice there is no index letter variable in here, so I'm just going to pull that out as my constant. And what's left would be 1. Remember, we have one of those formulas for the summation notation that states this. If we have some sort of constant, and the sum of that constant, all it would be equal to is c times whatever your upper number is, whatever your number is. So it's going to be 36 over n times n. So these cancel each other out. What we get is the limit as n approaches infinity of just 36. But what we have to remember with our limit properties is if you ever have a limit of some sort of constant, it's just going to be that constant. No matter how far you go with the n, it's always going to just be 36. Just to show you a quick picture of this, this is what we would have had. All right, when we would have sketched in the f of x equals 6, All right, there's our line there, and then I guess I'm gonna move this over. Here was that upper and lower bound. So here is my 4, here is my 10. It's bounded by here within those restraints. So what we have is a rectangle, basically, or actually in this case a square, where this width of our quadrilateral would be 10 minus 4, which is 6. This height, because of our function, is 6, and so this area would just be 36 as well. So if ever you can recognize this, these instructions gave you that you had to solve by the limit approach, but if you ever are in the position where you're just trying to find the area underneath a certain restraint or certain bounds, then you can always go ahead and try to recognize geometric figures and save yourself all this work. The next one that I'm going to do is number 15. You have quite a few problems like number 15, or a set of problems like 15. Okay, and I am actually going to rewrite this. I'm going to change that to addition and negate this, so what we have is f of x. Alright, and they do give you a sketch, but I'm just going to quickly review. If you ever have absolute values, remember the parent function looks something like this. It's a triangular shape that starts at the origin, and it would go over 1, up 1. If you plugged in -1, you would get 1. If you plugged in +2, you get +2. -2, you get +2. So it looks something like that. But you need to we had this section on transformations of parent functions, and if you ever have a negation not directly attached to the x, so it's on the outside of the absolute value function, so it's not directly attached to the x, that means it's a flip vertically. So this is what we would get. Something like that. And then also we have this addition, not directly attached to the x. That's a vertical shift, and it's positive, so we're going to go up 4. We're going to take this graph and move it up 4. So all in all, that is the transformed function. Your book gives you that exactly and perfectly, unlike mine. So I'm going to go ahead and sketch this. Okay, and what you'll notice is they didn't cut us off here. They didn't cut us off anywhere else. They had this shaded region that was right here. Keep in mind that we haven't had this, but the shaded region could go underneath the x-axis. But for now, what they've limited us to was -4 to 4. That's all that we have that's shaded. So what they ask us to do is set up a definite integral that yields the area of the region. They're still transitioning us into, can you look at this and determine what are you trying to find the area of? And here it's this function with respect to the x-axis, so that's actually going to be our function of interest. And then I am going to say dx because we are working, if you were to draw your rectangles, what these would be are up and down rectangles. So that means that we're dealing with the horizontal direction. So that kind of came out wrong. When you draw your rectangles, you would be dealing with up and down rectangles that you're moving with widths that are horizontal. So that's where we would come up with this dx. Okay, and then the next thing that we would do is draw in our little integration sign and just say that we're bounded from our lower to our upper, and that's it. That's a 4. Okay. We're eventually going to go through the processes of trying to figure out how to integrate this, or how to find the antiderivative of this function. But what I hope you can see is, if you ever can recognize a geometric shape and they don't give you instructions that you have to do it a certain way, just go ahead and say, well, I know what this would be. I have a base of a triangle that's 8. I have a height that's 4. And then I would just have to divide that by 2 to find the area of the triangle. This all in all would be equal to 16. On an AP test, that's all you would have to write. So it becomes very important you do have to remember how to sketch some of these old parent functions that have been transformed. All right. So everything that we've gone through, I just want to recap, is we learned the limit process of finding an area underneath a function. We use that limit process quite a bit, but now what we're starting to do is transition, because our integration process, this whole process that we learned in 6.1, not only finds us antiderivatives, but
besides that gives us areas underneath underneath some sort of function. So that's what we're transitioning into now. And then my hint to you is if you ever can form some sort of geometric figure, just go ahead and solve it by using some sort of geometric formula.